Wow, these are really straight lines. I wonder how they do it. Is it laser or is it a long ruler?
Wow! Did you see that car? I wonder how fast he was going. Hey, you know what? We could calculate that. I'm thinking we can figure out how fast that guy was going. Check this out. There's a car. There's a listener. And there's a car driving. Like this. Emitting a very annoying sound. I think we can use that sound. I've heard of something like this. The Doppler Effect. What is that anyway? Well, it's the change in frequency due to the motion of the source or the observer. This source was moving, and there was a frequency shift. Let's take a look at the Doppler effect. What's the math behind this crazy idea? Frequency of the frequency the observer hears is equal to the velocity of sound divided by the velocity of sound plus the velocity of the source times the frequency of the source. Well, I need to solve for the velocity of that source. Notice that the frequency of the source times the shift factor equals the frequency I hear. Let's solve for the velocity of that source. Do some rearranging. More rearranging. Almost there. Subtract V. Let's move over here. Let's clean that up a little bit. An equation. Velocity of source equals, there it is. Let's focus on that for a second. What are my numbers? In order to calculate the speed, we need an oscilloscope. Lucky for you, I just happen to have one. And now back to the calculations. Frequency that I observed was 2,961 hertz. The frequency of that actual horn, I know, 2,853 hertz. The Scion XD. Velocity of sound, 340 meters per second. Let's plug those numbers in. Let's simplify. Negative 12.4 meters per second. Why is there a negative? Because it's coming towards us. The distance is decreasing. 12.4 meters per second. Not too familiar with that. Let's multiply by conversion factor and get miles per hour, 27.8. 27.8 miles per hour. There you have it. 28 miles an hour? In the parking lot? Stop that guy!